Okay, good afternoon, everyone. So let's start. As we proceed toward the end of this semester, so I want to remind you first the homework 4 was released on last Wednesday, and this time we have 16 days to finish homework 4, and I believe the time is pretty sufficient, but you still need to do it earlier. And I saw a few discussions on Canvas about homework 4. That's really good. And again, if you have any problems, like programming assignment or in paper problems, do not hesitate. Come to the office hour, talk to TAs, talk to me, or post questions, and raise some discussions on Canvas. That's the best way, the most effective way to not only solve problems, but also to learn something. And the second thing I want to remind you is the final course project report. So I have briefly taken a look at the midterm report. It's really fantastic. So I think the remaining things you left is to keep up your good work and finish the course project. In the course project, you need to write down all the results you got and give the figures, give the tables, and give your thinking, your analysis, and what's your future work plan. And the due for the course project report, final course project report, will be April 27th. That's a Friday. And then the following Monday will be our final exam.
Will we get an exam patch?
What?
Session? I don't know. Session prep for the exams. Go over.
Oh, you mean review session for final exam?
Yeah.
Yeah.
Previous exam examples. I mean, we didn't have an exam. It's kind of hard to prepare.
So I can give you some guarantee the final exam won't exceed the homeworks. So all the problems you have done on the homework, I mean paper problems, is the superset of your final homework. Oh, no, final exam. So I would suggest you guys to review your homework solutions, and then by when we reach we'll approach the end of the semester, we will release all of the homework answers. And also, homework is open book. You can print out everything, but you cannot use electric devices. You can use calculator, that's for sure, but you cannot use any device which can connect to the internet. Any question?
What kind of calculators?
What?
What kind of calculators are approved?
Any calculator. Right? I would suggest you use a calculator on cell phones, because the cell phone can connect to the web, right? So you can use any other calculator. The old Casio calculator. I really use that before. I use it before when I was doing my high school.
You mentioned you're going to release the answers.
Yeah.
Are you also going to release code for
Code. We don't have code yet. So yeah, we mainly have we'll definitely release paper problems, the answers for the paper problems. Because in the final exam, you won't be asked to write down some code. There's no time for you to debug the code. But if you really want to see some example code for the program assignments, talk to me.
I just want to make my database.
Oh, okay. I'll try to find some piece of code for you. Okay.
You already said that contribute when you're trying to release those format answers, just so that no one can plan to study a little more.
Don't what?
Like when you plan to release those homework answers.
Oh, when?
Yeah.
Not right now.
Oh, right.
My current plan is to, at the end of the last lecture.
Oh.
The last lecture is April 2021 or 23rd, I forgot. And then you have 1 whole week for the review. So the deadline for the last homework 5, is the last lecture.
Okay.
So I won't rob your time in reviewing to prepare for the final exam. So if you can do your course project early and finish the submission of course projects even before the last lecture, then you have plenty of time for the review.
Thank you.
I said we have released every answer homework for the current 1, 0, 1, 2, 3 will be released later. So we will basically release the answer after we grade the homework.
Awesome.
Okay. Any other questions?
Are we still going to have 6 homeworks, or are we now only going to 5?
We have only 1 left.
Okay.
Yeah. So the counter starts with 0. 0, 1, 2, 3, 4, 5. So don't be scared. This is computer science stuff. They always start with 0. Any other questions? Okay, great. So let us continue with SVM. So today we're going to finish up SVM. So in the last lecture we introduced how we derive the dual form of SVM from a primal form. So that part takes a while and it's quite mathematically intensive. So today I will spend more time to review the whole procedure. You are not required to memorize it. You're only required to understand it. And when you look at the slides, you'll say, okay, I'm not reading something I totally lost. Right? And when we review, I just want to give you, just make sure that everybody understands the whole procedure, not to memorize the details. So how we obtain the dual form of the SVM from the primal form? So first we need to be clear what is primal form and what is dual form. Right? So primal form is, in general, some constraint optimization problem. Right? So in general, the primal form can be written as minimization of some objective function CFX, right? And subject to a set of constraints. So those set of constraints are represented by inequalities. So like J1x less than or equal to 0 until Gmx less than or equal to 0. Right? So we have m constraints here, and each of this G1, G2 to Gm are called constraint function. So this is called primal optimization problem, or primal domain, whatever. And to construct the dual form for this primal, we first do the Lagrange form. So this is a general strategy. So what is Lagrange form? Lagrange form is actually another function of x and of lambda. Lambda here corresponds to the Lagrange multipliers. So basically, for each constraint function, we introduce a Lagrange multiplier. So G1 lambda 1 into Gm lambda m. Right? So then the Lagrange function is represented as the summation of the original objective function plus the summation over all the constraints, where each summand is the product between the Lagrange multiplier and the constraint function. So this is a standard way to construct a Lagrange function. It applies to all kinds of optimization problems. And then we first convert this original optimization problem, constraint optimization problem, to a minimax. An objective function of this minimax is the Lagrange function. And inside this minimax is a maximum. It's max over the Lagrange multipliers, but we put a constraint that the Lagrange multipliers must be non-negative. And outside we minimize the Lagrange function with respect to x. But here x is free, right? No constraint on x. So the benefit of this conversion is that we remove the complicated constraints over x and replace it with a fairly simple constraint that's just non-negativity. So we have explained why this problem and this minimax problem are totally equivalent, right? So then what is the dual form? Dual form is simply switch the order of min and max. So if you just write max outside and also the non-negativity constraint of lambda outside and inside minimize x, and objective function does not change. This is called dual form. So we just follow this standard recipe to derive the SVM dual form. So this is so this part is our soft SVM. Right? We know that we introduced this slack variable CI to allow some example to break into the margin or even misclassify. Why? Because the data could be non-linearly separable, right? So we add some flexibility, right, to allow some incorrectly predicted examples. And then we first convert it into a minimax problem. Right? So those are the constraints. For each example, we have two constraints, right? So for each constraint, we should introduce a Lagrange multiplier, which is, say, for this constraint regarding the function margin, we introduce the multiplier alpha I, right? And for this CI, the negative CI, we introduce the multiplier beta I. And then we follow the recipe, we get our primal form, minimax. And then we just switch max min. Right? Switch to max min, we get the dual form. Dual form still looks complicated. And our next step is to simplify this dual form. How can we simplify it? Anyone remember? Anyone recall? What's our step two?
You optimize the error, the minimum, you optimize the error.
Yes. That's obviously to simplify it, right? You just because it's a max min, right? You first minimize and maximize. Now why not we first fix some alpha I, beta I outside, and try to solve the inner minimization problem. And then we use the solution of the inner minimization to replace this minimization. Right? Then we'll get simplified form. And then how can we minimize this Lagrange function with alpha I and beta I is fixed? We use gradient, right? We can compute the gradient with respect to the model parameters WB and those slack variables, right? We set the gradient to 0 and we solve it. Right? So these are only like the gradients only on linear functions, so it's pretty straightforward. And when you solve the gradient being 0, you get a few equalities, right? So we know that, okay, to ensure that inner part is optimal, right? The inner part is optimal, we must have our big vector is a linear combination of the training examples, right? So the training example is weighted by the Lagrange multiplier alpha I, and also the ground truth label yi. And similarly, we can obtain another two conclusions, the summation of all of i's is 0, and interestingly, Lagrange multiplier for each example, alpha I plus beta I must be a constant C. Remember, C is a hyperparameter. It's control the regularizer and the hinge loss. And then when we get this, right, we just substitute those for the original model parameters, you get the optimal solution inside, right? And then you get the simplified form, right? It becomes, it simply becomes a maximization problem because the inner minimization is replaced by its optimal value. And also you need to be careful that because if you this one can stay here only if this gradient must be 0. That means all those equalities must hold, right? That means those equalities must be constrained here. And then you just change you just remove the sign here, and so you turn the max to a minimization problem. You maximize the function is equivalent to minimizing the negative of that function. And also, because beta I never serves in the cost function, you can just remove it by adding some extra constraint, right? Because if alpha I is less than or equal to C, beta I is automatically satisfied the constraint, right? The negative constraint. And this is our due form. This is our final due form. So it's a typical projective convex optimization problem, and with some linear constraint and box. So you know the Lagrange multiplier, each Lagrange multiplier must be between 0 and C, and we need to ensure that the summation of all alpha I yi is simply 0. And also this function, this objective function is only with respect to our Lagrange multipliers. And all the other parameters are just removed. This is how we derive the due form. And this quadratic convex optimization algorithm, the algorithm to solve the quadratic convex optimization is pretty convex, pretty standard. You can find a lot of implementations in the web. Right? So you don't need to implement the optimization algorithm from scratch. And then the problem is that suppose we have run some powerful algorithm to solve this problem and get the optimal parameters out. How can we recover? How can we recover the optimal model parameters, the feature weights and bias parameter? So as we discussed in the last lecture, to recover the feature weights is pretty straightforward because when we solve the inner minimization problem, we have already get this equality, right? The optimal, the W must be a linear combination of the training examples weighted by the Lagrange multipliers. So you just substitute these alpha i's with their optimal values, you get the optimal feature weights. Then the problem, the really difficult problem is how to recover the optimal bias speed. So it turns out that by only using the conclusions when we solve the inner minimization, you cannot recover B. Then what kind of extra knowledge did we use to solve B? Yes, the KKT condition. This KKT condition is the center of the optimization, model optimization theory. So I hope that everybody has an impression on that. So when somebody talks to you about optimization, you can test them whether he has heard of the KKT condition. If he hasn't heard, it's just totally not an expert. It's outsider. So what is KKT condition? KKT condition is kind of testing condition. Right? So sometimes you can test whether if your optimization algorithm find out some input, and you can use KKT condition to test whether this point is some optimal. Or if you already know some points is some local minimum or local maximum, you can, according to KD condition, to derive some results about properties of those solutions. And for our case, the SVM case, KD conditions can serve both the sufficient and necessary condition to justify an optimal solution. So we can just use it without any differentiation. So the interesting conclusion or interesting conditions in KKD conditions is this complementary slackness. So basically it says, okay, if your optimization problem, specifically in SVM, can form a minimum optimal solution, then you must have, for each Lagrange multiplier and constraint function, their production is 0. This is a very interesting result. So basically say, okay, lambda m and this constraint function fmx cannot both be non-zero. At least one of them must be 0. And that's the key for us to recover the optimal parameter speed. Why? You can see, suppose we have run our powerful optimization algorithm to solve both the primal and dual form of SVM, right? And then from the KKT conditions, we can conclude that the complementary slackness must be satisfied. That means for any Lagrange multipliers, the multiplication between the Lagrange multiplier and the constraint function must be 0. Right? And also we combine with the conclusion when we derive the inner minimization problem. We actually get 3 types of the conclusions according to the when we reach the optimal solution of our SVM. So we just combine them together and to infer the optimal loss parameter. So the inference procedure is pretty straightforward. So we can look for some optimal Lagrange multiplier, say alpha G star, which is strictly between 0 and C. What's the benefit if alpha G star is strictly between 0 and C? So first, because alpha G star plus beta G star is constant C, right? So if alpha G star is strictly between C, we know beta G star is strictly above 0. Because this beta G star is C minus alpha G star from here. And now we know, okay, alpha G star strictly less than C, then beta G star must be bigger than 0. And then we look at the first slackness, complementary slackness. Beta G star is non-zero. That means the slack variable C G star must be 0. This is our first conclusion. And second conclusion is that because alpha G star is strictly bigger than 0, then look at the second type of slackness, complementary slackness. You know, okay, this part, this coefficient is non-zero. Then this term inside parentheses must be 0. So we get this term regarding the function margin must be 0. And the good news is that we know beta G star is 0 as well. Right? So now we can remove beta G star. And then because we know optimal W, right? And their only unknown parameter is just this optimal loss parameter. We solve it, just a linear equation. That's how we recover the optimal all the parameters, the feature weights, and the bias parameter from the dual solution. That's the whole procedure. Someone asked, what if like in some extreme case, right? So what if there is no alpha G star, which is strictly between 0 and C? How can we do that? So first, I can tell you, this is quite rare in the practice. At least in your homework 4, there's no such a problem. But what if you really need such kind of solution? What should we do? Right? We go back to the primal form. So look at this primal form. Remember, this primal form can be further reduced as regularizer plus the summation of the hinge loss, right? Because we can remove the slack variables. So it's a summation, this is the C outside, summation over this hinge loss, 1, 0, 1 minus the function margin. Right? Now you just substitute W with the optimal values, we know that. Right? Then you just optimize this. This is just an optimization problem over scalar. You can use your stochastic subgradient to do that. Or you can use whatever other optimization algorithm you want. So the most general way to solve the optimal path parameter.
There's something I guess I'm not quite understanding, but if you go back to your last slide, when alpha G star is greater than 0, that means that that example is in the margin, correct? Or is, yeah, it's inside the margin. And so then why is the slack variable 0? Why, yeah, why is G star 0?
It is possible, right? We do not say, okay, if your alpha G star is bigger than 0, then what's the possible position? Alpha G star is bigger than 0 means that it is a support vector, right? What's the position of support vectors? They are inside the margin or stay on the margin. So actually, this is some special cases of the support vectors. We require, so in this case, we know this equality holds. That means the function margin is 1, meaning that those support vectors directly stay on the margin. Yeah. So the support vectors can be categorized into 2 types. One type is directly stay on the margin. The other is intrude the margin. It's the inside margin. It contains both. But usually it won't be like extreme case like, okay, there's no points directly stay on the margin, but all the points are inside the margin. This is not possible. Why? So why I say it's very rare. So it's interesting. So you see, this is the examples of the support vectors, right? So those points which directly lie on the margin can be used to recover the loss, right? As we just mentioned, because the function margin is 1, the equality holds, right? But those points is less useful to do that. Right? But if you say, okay, what if there is no alpha J which is strictly between 0 and C? That means, okay, among all the support vectors, the position of support vectors all stay inside margin. So this is usually very rare. I cannot say, okay, it's not possible. It's very rare. Why? Because if you can imagine, like, if all the points stay inside the margin, why not I further squeeze this margin to touch some points? If I squeeze this margin to touch the most outside points, the support vectors, you can even enlarge the margin, right? So that's the case. But I cannot for sure because the hyperparameter C is tunable. Like you can intentionally like set C to be very small and even ignore the hinge loss. Then in some cases it still could be possible. Any other question? So by the way, what are support vectors? Support vectors, I want to emphasize again, support vectors are those input examples, or training examples whose alpha G star is strictly bigger than 0. And why we call it support vectors? Because according to our conclusion, right, W star is the optimal feature width is a linear combination of the input example weighted by the alpha G stars. Right? So if alpha G star is 0, then this example does not account for the optimal feedback. We can just throw it out. So any questions so far? So everybody's good? Okay. Okay, so let us continue. Let us look at the kernels and the kernel trick. Kernel and kernel tricks is a key for us to generalize SVM to nonlinear SVM. So from the general rule to perform classification for linear classifiers, we know we take the sign of the classification function, right? So classification function is inner product between the weight vector and test example plus a bias parameter B. But from the dual form of SVM, we know that optimal weight vector is a linear combination of the training examples weighted by these Lagrange multipliers. Now, if we substitute W star with this linear combination, we can get that the inner product between the weight vector and the test example is the summation, where each summand is the inner product between each training example and test example, and weighted by, of course, alpha I star, the ground truth label of ith example yi. Right? So with this representation, to predict the label for an input x, we only need to compute the dot product, the inner product, like same thing, between the training examples and new example x. We do not need to explicitly recover W star, in fact. And this is true even if we map examples to some high-dimensional space. So why do we consider to map the input examples to high-dimensional space? Okay, linear, nonlinear classifier, right? Yeah. So we mentioned in the last lecture, right? So some common strategy. So what if the data in the original feature space is not linearly separable, right? We want to learn a nonlinear classifier to well separate positive from negative examples. What shall we do? A common used trick is that we work out some smart nonlinear transformation. We map the original features into a high-dimensional space. And those high-dimensional feature vector is a nonlinear transformation of the original feature vector. So in a high-dimensional space, we expect that those data points can be linearly separable. So we can learn a linear classifier in that space. So now we can see by using dual form of SVM, right? We can first, if we want to perform nonlinear classifier, right? We can first work out some nonlinear feature mapping over the inputs, and then solve the dual form in a high-dimensional space. And then when we do the prediction, given a new input x, we first perform the nonlinear feature mapping, and then compute this inner product by this summation. And in summation, each summand is the inner product between the mapped vector for each training example xi and the mapped vector for each test example x. So if we, for simplicity, we can define this inner product as a function of x of z, which is to first perform nonlinear feature mapping on x and z, and then calculate their mapped, the inner product of their mapped vector. And then to compute the prediction after this high-dimensional lifting map, right? We can just use this one, right? Right-hand side. So the prediction rule becomes a summation, the bias parameter plus a summation over all the training examples where each summon is the inner product between the mapped vector of the training example and the mapped vector of the test example weighted by this R bar. Any questions so far? Everybody's good? Okay, so, but here is the problem, right? So although this way looks kind of succinct in that, okay, we do not need to explicitly recover the feature vector in a high dimensional space, right? But it incurs the computational cost. Why? Because previously, if we recover W, right? If we recover W, when we do the prediction, we can just map the feature vector and do one inner product. So now, if we do not recover W, then we do the prediction. We need to calculate the inner product between each feature, between each training example and test example. And also, before we calculate inner product, we need to do the nonlinear feature mapping first. So that's a severe problem. So if we have to compute this feature mapping every time, annually, right, then we gain nothing from this formulation. What's the benefit of this? And what's the benefit of SVM due? Except that we know, okay, what are support vectors? And let us consider an even like extreme case. What if our feature mapping is so high dimensional such that you even cannot store that feature vector? Say, suppose your feature vector is 1 trillion dimensional. Then your feature mapping, your explicit feature mapping inner product will be very, very time consuming. Even if you want to map, if you want to recover the feature vector in the mapped feature space, you need to store and maintain a 1 trillion dimensional feature vector. That's impractical. And going further, what if your feature mapping is infinite dimensional? So if your feature mapping like maps your original like 3-dimensional feature vector into an infinite dimensional feature vector, you cannot finish the computation in practice. How can we address this problem? So naturally, we want to ask if we can find out a proxy of this inner product computation. Let us say this proxy is just a function of the input x and z, such that the evaluation of this proxy function does not need to do any explicit high-dimensional feature mapping and then do the inner product, but the result is exactly the same. This is called kernel trick. So this is called kernel trick. So then the natural question is, do we really have such kind of proxy function? We do not need to do explicit nonlinear feature mapping and do the inner product. I just need to evaluate in the original feature space. Then we get everything. So we can see one example here. So the example here is called polynomial kernel. So let us assume we want to map the 2 examples x and z to a high dimensional space. We do the quadratic map. What is quadratic map? So suppose we have n features. Then we first, in our map feature vector, we first construct the degree 0 term, which is simply 1. And then we append the degree 1 terms. which is simply a replicate of all the original features. You can consider as x1 take the power of 1, x2 to the power of 2, x2 to the power of 1, to xn to the power of 1. So this is called a degree 1 term. And next, we construct the degree 2 terms. So what are degree 2 terms? You just do the cross production among all the features. So you get x1 squared, right? x1 multiplying with itself. x1 squared, x2 squared until xn squared, and x1, x2, right? Cross product. x1, x3 until xn minus 1, xn. So this is called a degree 2 expansion or quadratic expansion. So question. Now, after the feature mapping, what's the length, what's the dimension of the mapped feature vector? What's the scale of the dimension? You don't need to calculate the exact number. What's the scale for that? Suppose originally we have an n-dimensional feature vector, right? So after this quadratic feature mapping, how many features do we have? Just give me a scale, not the exact number.
Q.
Q? Why is Q?
It's not the degree 2 terms, but not just twice as many.
They're just degree 2.
Oh, just degree 2.
I heard that. Can I say it?
About that square.
Yes. Right. Why? Because we have degree 2 terms. 0, 1, degree 0 term just 1, right? Degree 1 term just n features, right? But degree 2 terms, we need to calculate the cross product between among all those n features. Right? So n features multiplying with another n features, you get n squared terms. Although you need to do the deduplication, right? But roughly, after this quadratic feature mapping, you get number of features proportional to n squared. So you can imagine, like, if you have 1,000 features, then this dimension of the mapped feature vector will be approximately 1 million. It's a very high dimension. Of course, after this nonlinear feature mapping, I don't want to calculate inner product between the mapped feature vector. That's really costly. Then, can we find out a smart proxy function? By evaluating this proxy function, it is equivalent to do the feature mapping and inner product, but we never explicitly do that. And the answer is yes, and we have such function. This function is simply as this: 1 plus the inner product between x and z, then take square. So we can see the evaluation of this function is only inside the original feature space. You calculate inner product between x and z, right? And you plus their inner product and take square. So if x and z are both n-dimensional feature vectors, so what's the complexity of their inner product? So if x is 100 dimensional, z is 100 dimensional, what's the number of operations to compute x transpose z? An idea? What? Yeah, 100, right? So what is inner product? Inner product is to just do the element-wise product of the two vectors, right? So you have 100 elements, and you do 100 elements product, and then you just add them together. 100 plus 1, right? So the time complexity is just the O(n). N is the dimension of feature vectors. But if you map them to this quadratic feature space, right? Because after feature mapping, the length or the dimension of the feature vectors are n squared. Right? Then you calculate the inner product. It will take O(n) squared complexity. So now you see the difference. Right? And now let us check whether these two feature mapping, these two methods will end up with the same result. So to see this, I want to show you the example. We can compute together. We can compute together. Suppose our original feature space is just a 2-dimensional. It's just 2-dimensional. Right? And I have two feature vectors, x and z. Right? So phi x, just copy the terms here. We have 6 terms here, right? 1, x1, x2, x1 squared, x2 squared, and x1, x2, right? And similarly for the mapped feature vector for z, we have 6 features as well. 1, z1, z2, z1 squared, z2 squared, and z1, z2. So remember, x is x1, x2, z is z1, z2. It's a 2-dimensional space. And now we compute the inner product. Inner product after the feature mapping. How can we compute? Element-wise product. Right? You just multiply 1 with 1, x1 with z1, x2 with z2 until x1, 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 x2 with z1, z2. Right? Add them together. That's why the complexity is proportional to the length of the vector. So 1 plus x1 z1 plus x2 z2 x1 squared z1 squared x2 squared z2 squared plus x1 x2 z1 z2. We use 6 operations or 7 operations. And now let us try to compute this proxy function. So now I want to use this function to replace the explicit inner product. We can try to compute that. So first, what is the inner product between x and z? You can read it out. What is the inner product between x and z in that original feature space? Yeah, it's simply x1 z1 plus x2 z2, right? Because we have only 2 features in our space. Then you plus it 1 and then take square. Now let us try to expand this square term. The expansion is you just follow the rule. You just you first compute the square term for each element here, right? So we have a 1 square of x1 z1 square of x2 z2, and then the remaining terms are just cross product. You just multiply different terms and multiply a constant 2. So cross product between 1 x1 z1, 2 x1 z1, and cross product between 1 x2 z2, 2 x2. And finally, cross product between this term. So it's 2 x1, 2 z1. Now let's compare the result. The result here and the result here. What can we get? we can find the exact match of all those terms, except some constant coefficient. So 1, x1, z1, or x1, z1, although I have 2 as a coefficient here, but actually this coefficient does not matter at all. And x2, z2, this square term, x2 squared, z2 squared, x2 squared, z2 squared, and finally, the production of all 4 terms. So you can see the summation in the 2 results, they align with each other, except some constant coefficients. But actually, we do not care about these constant coefficients. Why? Because I can simply manipulate this phi z, this mapping, by adding constant in front of the quadratic terms. If we do this, then even the coefficients match as well. So now we can see, by simply evaluating this proxy function, you get the same effect as explicit feature mapping and then do the inner product. But the computational cost is much less, right? If you want to compute this, you only need to compute the inner product in the original feature space. That is a 2-dimensional space, right? And then add a constant and take square. So it's still proportional to the dimension of the original feature space. But if you do the explicit feature mapping, your mapped feature vector has dimension squared to the original dimension. Then you do the inner product. The time complexity is squared to the number, to the original feature number, right? So there's a huge difference in the computational cost, although the results are almost the same. Any questions so far? So everybody is good, right? So that's the kernel trick. Essentially, kernel trick is to use some proxy function to replace the explicit computation of the feature mapping and inner product. And this proxy function is called a kernel function. So we can go back to our slides. So what is kernel trick? If you want to compute the explicit high-dimensional feature mapping on 2 input vectors, x and z, and do the inner product. And to achieve this goal, we compute a kernel function, which only performs operations in the original feature space without any explicit feature transformation or mapping. Then we call it kernel trick. So it is essentially a computational trick. And the benefit is, as we just mentioned, right? So for this quadratic feature mapping, we know that explicit feature mapping and the inner product will take n squared. This is the exact number of operations. If you want to calculate, you will get this number, but it's roughly proportional to n squared. But if you use the kernel function, as we just mentioned, right, to compute, the time complexity is just proportional to the number of features n. The results are the same. That's the kernel and kernel tricks. So any questions so far? Okay. So next, let us look at the properties of kernels. In other words, the property of kernel functions. So as we know, okay, there are so good properties of kernel function. And I want to ask, are any functions or kernel functions? Can we use any function of 2 input vectors as kernel functions? Any idea? Just give me a guess. What's your intuition? No. Yeah, of course, right? If it is yes, then we have already solved the nonlinear classification problem. There's no need to investigate so many error codes. Of course, you cannot use arbitrary function as a kernel function. So a function is a valid kernel function if it corresponds to some nonlinear feature mapping and then do the inner product. So the strict way to prove that the function is a valid kernel function is that you find out an equivalent feature mapping and then prove that the value of this function is just the inner product of the mapped feature vectors. But usually it is very hard to find such a mapping. It's really very hard. And given that you can construct, as later we'll say, there are many rules to construct new kernels based on existing kernels. It's very hard to do that. So there's another commonly used method to justify a kernel function is valid or not. It's based on the Gram matrix. The Gram matrix is built on a finite set of input vectors. To introduce Gram matrix, let us first review the positive semi-definite matrix. So what is positive semi-definite matrix? Any impression? If you don't recall, just read the slides. Right? Mm-hmm.
So positive semi-definite is where you take any vector, you apply the matrix to that vector, and times the result by the transpose to the vector, you get something that is non-negative.
Yeah, that's the what you recite is exactly. This is the definition of positive semi-definite matrix. Of course, there are many properties of positive semi-definite matrix, like non-negative eigenvalues and whatever, right? That's the advanced properties. The basic definition is here. We say, okay, a symmetric matrix M is positive semi-definite if for any non-zero vector Z, we have this quadratic form, non-negative. So for any non-zero vector Z, we have Z transpose MZ. MZ is vector. And then Z transpose is a scalar. So this value must be non-negative, always non-negative. Then we say, okay, this matrix M is positive semi-definite. And then let us look at the definition of Gram matrix. So Gram matrix is built on a finite set of vectors. So we denote it by S, consists of n vectors, x1 to xn. And Gram matrix is an n by n matrix. So n is the number of vectors in S. Each element of this Gram matrix is an inner product between x and xj. This is called Gram matrix. And Gram matrix is positive semi-definite. So this is actually pretty. If you have some time, you can write down the form of Gram matrix, and it's pretty straightforward to show the semi-definites of the Gram matrix. So we know, okay, Gij is xi, xj, the inner product, right? So if you write down x, all the n vectors, you stack them into a matrix X, right? So you can write the Gram matrix is GXX transpose. This is just the verification. You can do it. And then you can show that for any non-zero vector Z, you do this Z transpose GZ is equal to Z transpose X transpose Z. So we say this is actually the inner product between two vectors, between the same vectors. So it's always non-negative. Any questions so far? Everyone's good? Okay, so because Gram matrix is a positive semi-definite for any vectors, right? So even if I perform some nonlinear feature mapping on those x, phi x1 to phi xn, no matter how long this map feature vector, even infinite dimension, doesn't matter. Because the size of G is only determined by the number of vectors. Right? And we can always show that the Gram matrix is positive semi-definite. Even if you apply some nonlinear feature mapping here. So that reminds us, right? So to check whether a function k, function k of x and z is a valid kernel, I can evaluate the kernel function over this n input vectors as well. Right? I can get a kernel matrix. I can get kernel matrix big K, such that each element is a kernel function between of x and xi and xj. If it is a valid, if this is valid kernel function, then we know there must exist some feature mapping such that the kernel function is equal to the inner product between the mapped feature vectors. In other words, the kernel function must correspond to the kernel matrix must correspond to some Gram matrix. Right? And then, because Gram matrix is always a semi-positive definite, then the kernel function should always be a semi-positive definite as well. Does it make sense? So that comes up the way to prove whether a particular function is a valid kernel function. You just enumerate all possible finite input vectors. And for all the input, for each finite set of input vectors, you can calculate kernel matrix. And to verify whether this kernel matrix is positive semi-definite. If for an arbitrary set of finite vectors, the corresponding kernel matrix is semi-definite, then we can conclude this kernel function, or this function is a valid kernel function. That's the idea. Does it make sense? So, to summarize, right, we have two ways to prove a function is a valid kernel. The direct approach is to just find out the underlying mapping. Right? If you can find out the underlying mapping and show that, okay, the function is equivalent to the inner product after feature mapping, you're done. But if you cannot do that, you can compute kernel matrices for any finite set of vectors and to verify whether the kernel matrix is a positive semi-definite or not. So someone may question whether this is kind of rigorous, right? Of course, what I say is just kind of a reasonable reasoning. It does not necessarily represent a kind of rigorous proof. And fortunately, the proof has already been done by others. This is called the Mercer's theory. So what is Mercer's theory? That the function of x and z be an arbitrary function that maps two n-dimensional vectors to a real number, then this function is a valid kernel function if for every finite set and for any choices real values, we have this double summation over ci, cg, and kernel function over xi, xj non-negative. So what does this mean? An idea? That requires us to try to put everything into a matrix and vector world, right? So if you represent a vector C, right? has the vector consisting of all those coefficients, C1, C2 to Cn. Then, and also we compute the kernel matrix K. Then, this double summation is simply the quadratic form C transpose K. C. You can verify it. You can verify it. So basically, they use this condition is the same thing to say, okay, this quadratic form is the negative. So it is exactly what we have said. What we have just said. Any question?
I understand this correctly, that's just a fancy way of saying A is semi-positive definite.
Yes. That's it. Nothing else. But as I just mentioned, my reasoning is kind of intuitive. But if you want to give a strictly proof, you need to prove that for any finite set of inputs, the kernel matrix is non-negative. That you can imply that this is a valid kernel function. This is from finite space to the infinite space. So you need some rigorous proof. This is but fortunately, the proof exists. It's a very important proof for the kernel method. Kernel method is a branch of machine learning. Any questions so far? Okay, good. So here are a few commonly used kernel functions, like polynomial kernel. One special case of polynomial kernel is called linear kernel. You just do the inner product between x and z without any nonlinear feature mapping. This is also called kernel. But you do the feature mapping in original space. Right? But in general, you can take the inner product of x and z to the power of d. And then you add a constant c. Then if you can expand those terms, after doing this, you will say, okay, those summation include all terms which represent interactions of order d or lower. It's commonly used the common form for polynomial kernel. A second popular kernel, or even more popular than polynomial kernel, is called Gaussian kernel. You will use that to develop your nonlinear SVM, because in most cases, Gaussian kernel can yield enough satisfactory results. So what is Gaussian kernel? It's just like the Gaussian distribution. You first compute the square norm of the difference between x and z, and then divide it by a non-zero or non-negative constant c, take minus, and take the xp. That's the Gaussian kernel. And here, this square norm is a squared Euclidean distance between x and z, right? And c is a free parameter, and it's not hard to see that if you have very small c, then then 1 over c, or this non-zero numerator over c will be very large. So if x is not exactly as c, then this term inside the exponential could be very large. You take exponential of the negative of this large value, you approach to 0. So that's why when you use very small c, your kernel matrix is close to an identity matrix. And similarly, if you have very large c, you can verify it's a k is approximate to unit matrix. This is a Gaussian kernel, and I'll give you some interesting exercise. Right? Can you extract the underlying feature of the Gaussian kernel? I can tell you the underlying feature mapping for Gaussian kernel is infinite dimensional. It's an infinite dimensional feature mapping. Your mapped feature vector is infinite. And given a set of kernels, you can use a few rules to construct new kernels. Like you multiply the existing kernel function by a constant, positive constant. It's a new kernel. You multiply the existing kernel function by a function applied to both inputs, you get a new kernel. Or you apply a polynomial kernel you apply a polynomial function over the existing kernel function, you get a new kernel. So basically, there are quite a few ways to construct kernels. I won't list them out, right? So you can just check out the slides. So basically, if you in practice, you'll never it's never necessary to construct a kernel function from scratch. You can always pick up some not commonly used kernel and then use those rules to combine them together to form a new kernel. And the validities of those rules have already been proved. So now we have reviewed the properties of kernels. And finally, how can we get our nonlinear SVM? So in practice, people rarely use linear SVM. We usually use nonlinear SVM. The key step is very simple, very straightforward. Given that you know what is dual form, you know what is kernel tree. So this is our dual form, right? So the key in the dual form is that we have a double summation where inside each summation there's an inner product between each pair of training data xi and xg. Now, suppose we do some highly complicated nonlinear feature mapping and we do not want to explicitly compute this mapping. According to kernel trick, we replace the inner product with some kernel function. That's it. Then we solve this dual form with which contain the kernel function. We're doing nonlinear SVM learning. Any questions so far? Just one step. So now we can see the usage of the dual form, right? So if we perform a nonlinear feature mapping to an infinite dimensional space, you cannot explicitly represent, update, or compute the bit vector couple. Oh, sorry, here there is no bit vector couple. But by using kernel tree, you can still do everything. You can still obtain alpha values. And during the prediction, we do not need to recover the original feature bit vector. We just do this. So everything is computed in the kernel. We never need to compute explicit feature mapping. Then how can we identify the support vectors? An idea? Suppose we have modify our dual form by applying the kernel tree here, right? And now we have solved this quadratic convex optimization problem to get optimal alpha I values, right? And how can we obtain the support vectors? Any suggestion? Just give me a guess. How can we get the support vectors? Oh, how do we know which examples are inside the support vectors?
The alpha values are positive?
Yeah.
Or those?
Yes. Nothing changed. You just take a look which optimal alpha values is bigger than 0. Right? Same thing. The only difference is that we cannot compute support vectors after their feature mapping, right? Because the feature mapping could be infinite dimensional. But in most cases, it's not necessary to know that. We're just curious which subset of examples decides the model. So there's nothing different after we apply a kernel function. The second thing is that how can we recover? Because in the prediction, we need to know the box from B, right? And how can we recover B? How can we recover B? If we perform some non-efficient mapping to some like infinite efficient space, how can we recover B?
Use KKB.
Yeah, of course we can use KKB. And then? Think about it. It's important because you are required to implement nonlinear SVM with this Gaussian kernel. So actually, even if you use a kernel tree, there's nothing changed. Right? You can imagine this is just a inner product between two mapped feature vector, right? So the way to recover everything is the same as before. Right? So how can we? Because of this representation of W, we do not need to explicitly recover W, but we do need to recover B. Right? But the way to recover B is exactly the same as before. We find out those optimal Lagrange multipliers between 0 and 6. Right? If you do remember, let us go back to the slides. It's here, right? So we find out some optimal Lagrange multipliers strictly between 0 and 6. We know this equality must hold, right? Function margin must be 1. But of course, W star is unknown. We do not need to recover them. But we know W star transpose Xj. How can we compute W star transpose Xj? Use the kernel tree. Okay. So W star is a summation of alpha J star, Yj, and Xj. Okay. And now you do the inner product with Xj. Alpha J star, and kernel function between Xj and X. Okay. Of course, you must multiply with Yj. Then you solve this, right? And how do you get B star? Use Yg minus this in the product. That's it. Any question? So basically, you use exactly the same way to recover the box parameter B here. The only difference is that because W star could be infinite dimensional, we cannot explicitly compute this W star transpose Xj star. Now how can we compute it? We use kernel tree. Because we know that W star is represented as the inner product, not inner product, the linear combination of the training example, right? And then you just replace W star with this linear combination, you get this inner product as the summation over the inner product to each training example and test example. Then you just replace the inner product with the current function. You get B. And then you can do whatever you want. Any question?
I was just going to ask, are you going to post those slides that you prepared the notes on?
If you want, I can post.
I would
Is everybody like these slides before these slides? Okay, okay. Yeah, I'll do that. So I need to make a note here. Kernel tree. So last minute. Just want to show you the distribution of support vectors here. This Gaussian kernel. We know the support vectors in the high-dimensional space will stay on a hyperplane, right? But in the original space, it can only stay on some nonlinear curve. That's the example where the support vectors stay and use Gaussian kernel. Okay, we have finished everything about the support vector machines. I hope everybody understand that. And if you have any question in homework 4, especially in implementing nonlinear SVM, do not hesitate to post the questions on cameras or come to the office already.